This video will show the key concepts of the time-trigger network-on-chip based multicore prototype that has been developed by ICA4 Ikerlan in the scope of the FP7 MultiPARTES project. This project is aimed at developing tools and solutions for building trusted embedded systems with mixed criticality components on multicore platforms. Most of the currently available commercial multicore processors are homogeneous. This means that all of the cores are identical. That is, they have the same architecture and consequently they have the same computing capabilities. As a result, these processors are not well suited to target the wide range of different applications existing today. In order to fill this gap, heterogeneous multicore processors have been proposed. These include different cores with distinct architecture and computing capabilities. In the specific case of the MultiPARTES project, we envision a heterogeneous multicore processor that comprises 2 Intel x86 and 3 Spark-compliant Xeon cores. The formers are to provide performance while the laters provide reliability. Hence, safety-critical computations are to be executed by the Xeon cores and regular calculations are to be performed by the x86 cores. This processor has been built using 2 separate boards. The Xeon cores are hosted in a Xilinx Spartan 6 FPGA, while the x86 cores are available in a commercial Intel Atom. Both devices are interconnected by means of a PCI Express link. In order to gain performance, the 2 x86 cores are tightly coupled by means of a shared cache memory in the Atom processor. On the other hand, the Xeon cores are isolated each other in the FPGA in order to increase reliability. The objective here is that a single fault affects only one of the cores. Hence, each Xeon core is autonomous with its private memory and peripherals. Moreover, as these cores are soft, they can be tailored to the specific needs of the target applications. Intercore communication is a key aspect to be considered in such a heterogeneous multiprocessor. Indeed, communications might make the system unpredictable if they are not conveniently performed. It may happen that a given core occupies the communication infrastructure for too long, provoking that other cores fail to exchange their data on time. In order to ensure predictable communications among the safety-critical cores in MultiPARTES, a time-trigger communication infrastructure is implemented. Each core is allocated with predefined and fixed slots of time to communicate data, regardless of the overall traffic on the network. Hence, the maximum communication delay between any two cores can be known with precision. The amount of time slots assigned to each core depends on the required communication bandwidth. The communication solution adopted in MultiPARTES is a time-trigger network-on-chip. This TTNoC includes a set of interconnected switches that route the data packets in the 4 directions based on the routing information included in the packet headers. This way, a data packet can be delivered from any sender core to any receiver core. The TTNoC implemented in MultiPARTES comprises 4 switches. 3 of them are connected to the 3 Xeon cores and the remaining one connects to the PCI Express driver, which ultimately enables communications with the 2 x86 Atom cores. The FPGA hosts thus the Xeon cores and the TTNoC infrastructure. This is the communication schedule in the MultiPARTES multiprocessor. Note that some of the data exchanges are carried out simultaneously through the TTNoC using separate switches and links. Indeed, performance is one of the key benefits of a network-on-chip. Despite the convenience of using a network-on-chip in the current implementation with only 3 on-chip cores can be a matter of discussion, this solution is adopted due to its good scalability in light of future massive multicores. A conflicting issue to achieve isolation among the Xeon cores has its roots in the necessity of sharing an off-chip memory. If no specific considerations are taken, it might happen that a corrupted core overwrites the data previously written by another core. In order to cope with this problem, a deterministic shared memory controller is proposed. This DSMC assigns separate memory segments to the cores and processes the memory access requests delivered by them. These requests include type of access, read or write, address, and for writing accesses data. The DSMC identifies which core is requesting a memory access based on the reception time of that request, and uses the address contained in the access request as the relative address within the memory segment assigned to that core. If the relative address overflows the size of a memory segment, then that access is aborted. In this example, one of the Leon cores, core 3, acts as the DSMC. The remaining two Leon cores publish 2 and 3 values respectively, and the Atom publishes 4 values. The cores alternatively request write and read operations to the DSMC, and thus the value sent to it is later received back. Every core receives the values published by the others and outputs them to a screen. Additionally, the Leon cores control two LEDs which blink at the rate set by the value received from the DSMC. Finally, when pushing a button connected to these cores, the published value is increased by 1. This simple experiment allows us to check that inter-core communications are successful in the MultiPARTES multiprocessor. Let's see this in the real prototype. This is the output of the Leon core. And this is the output of the Atom processor. We see the default values 2, 3, 4. Here, we see the LEDs blinking 2 and 3 times per second. Now we push 3 times the buttons connected to the Leon cores, increasing the published values. In effect, note that the values published by the Leon cores are now 5 and 6, while the Atom continues to publish the same value 4. The second example is to check the correct functioning of the DCMC. By default, the address field in the memory access request issued by the cores is all zeros. Therefore, read and write operations are carried out on the lowest memory position within the segments assigned to the cores. By triggering a microswitch, the address field in the memory access request is set to all ones, forcing write and read operations be performed in the highest memory position within the segments. Finally, by pushing a button connected to the DCMC, the address is increased by 1, provoking a segment overflow. This is detected by the DCMC, which lights a red LED. We return back to the prototype, which continues to be in the same state we have previously ended in. This time the Leon screen is connected to the DCMC. Now, we trigger the microswitch to force memory operations in the highest address within the segment. We check that everything continues the same. Finally, when increasing by 1 the address, the DCMC lights the error LED and indicates the segment overflow in the screen.